need to choose what happens if yt is here or there. And I will be explaining it in a moment, how we can use this. Okay, so yt could be like this. Okay, so how am I going to couple? I'm about now to pick k from here and k from there and switch. And I'm about to pick k from here and k from there and switch. But I want to have some correlation between the moves that I do here and there. So for the moment, just for this step, I'm going to start enumerating my balls. 1, 2, 3. Did I forget something?
You have 2 4s.
Is it 5?
Where is the 5? Oh, here. Thank you. Oops. Okay, so I start enumerating the white balls. 1, 2, 3. Now I'm out of white balls. I go to the red 4, 5, 6, 7. I do the same thing. I start enumerating the white balls. 1, 2, 3, 4, and then 5, 6, 7. Now I start with 8. So 8, 9, 10, 11, 12, 13, 14. And then here 8, 9, 11, 12, 13.
8, you skip 10.
God. It's so hard to do this in front of people. 11, 12, 13, 14. Okay? So now, instead of picking balls, I'm going to pick indices. Okay? So pick k indices from, let's say 7, just on our example. In the general setting, it will be from 1 through n. And then pick k indices from 8 up to 14. And switch the balls that are labeled by these numbers. Okay? This is how I'm going to be coupling this. Why? Well, there is hope that maybe I will move this 4, and maybe I will not move the 11. And if that happens, then these two things match suddenly. Okay? Can we understand what I'm trying to say? So the general setting says pick indices from 1 through n here, and then n plus 1 to 2n. That will be the general coupling. Okay, so the question now is, with what probability do they match after 1 step? Do they match after 1 step? Well, they match, as we said, if we pick a non-matching pair here, but we don't pick the non-matching pair over there. Or the other way, if I don't pick the matching pair here and I pick the matching pair there. So this is twice. So n choose k squared. And then, let's say I picked the matching pair over there, so I only need to pick k minus 1 more indices. And here, so there I picked it, and here I didn't pick it, so this is n over k, n minus 1 over k. N minus 1 choose k. Okay? And this gives this odd number that you see over there, 2k times n minus k over n squared. Okay, suddenly we start seeing this number that appears here, and it makes a little more sense. Okay, so that's, any questions so far? Okay. Okay, so let's bring this, how can we use this information? With any other move, by the way, the distance remains 1. Still, we are adjacent in this graph. Okay? Right? Any other move, they're not going to increase their distance. Okay, so this means that if at time t, the distance was 1, then the expected distance after one step is 1 minus this number. Okay, because with this probability the distance remains 1, and with this probability the distance becomes 0. Yes?
So in your analysis, why is it sufficient to look at the y neighboring?
I'm about to explain this right now. Give me 2 minutes, and if I haven't answered your question, then I'll come back to it. Okay, but for neighboring things, we can see what's going on, right? So what happens now is, assume that xt now and yt were not adjacent. They're far away on the graph. So what I'm going to do to couple them, this is what path coupling is, and this is due to Bernoulli and Dyer as a technique. Now, I do my Markov chain here, so I chose k indices, and I went to xt plus 1, right? Now, I'm going to do this coupling with this neighbor. So this, let's call this x1. This will go to x1 t plus 1. This, now, I did a move here according to this path coupling, so this will go to x2 t plus 1, and so on. And by keeping moving on this path, I will eventually say, hey, what is this guy doing? And it will be determined by what the previous guy did, which was determined by what the previous guy did, and so on. And the fact that the expected distance decreases, that means that the distance here will also decrease in expectation. So let's see how this works. So, okay. So meaning that here, each thing will decrease with this expectation, so I'll be adding those things. So the probability that they haven't coupled yet will be less or equal. What is the worst distance between these two guys? It's n. And then having this thing occurring again and again. So okay, so this is what path coupling says. So that's the difference between path coupling and coupling. For coupling, I would have to general states. They're far away, and I would have somehow to determine how to couple the moves. If I do something on one, okay, what is it that I do on the other? But for path coupling, they say that no, look only on adjacent things, if possible. And this, if you manage to do something on adjacent sides that is a coupling, meaning that I haven't forgotten any moves of the Markov chain here, and the expected distance is less than the starting distance, then this coupling on the neighboring things can extend to general sides that are not neighboring, and you can have a coupling. That's what Bernoulli and Dyer have done. And we followed their technique. We applied it for this case by creating this specific path coupling. Okay? And so now this, remember that the tunnel variation distance is bounded by this. So now we just want to bound this by e to the c, and this is the choice of this coefficient reversed, and then log n to kill this guy, plus c times this term again, to make it less or equal than e to the minus c. Okay, so here we use the fact that, remember, 1 minus, that this thing is something like, actually less or equal than 1 over e, something like that. Okay, so this is the standard inequality that people use on this type of card shuffling. Okay? So this is how you prove a theorem like A.
So that's the same technique that the Collins et al. Used?
No.
Okay, good one. Different.
It's very different. So they used the technique that this part tries to imitate. So what they did, they used representation theory, spherical functions, They said that, hey, the eigenvalues and eigenvectors for these things are the dual Hahn polynomials. It's just that one parameter on the dual Hahn polynomial was 1, so many of the things got killed, so you had very, very smooth and nice formulas. And then you could use the L2 norm to bound the total variation distance. So remember, the total variation distance is just the L1 norm. So if you square it, that is bounded by the L2 norm of this thing. And this basically is the sum of the eigenvalues of that matrix to the 2t times the first entry of your eigenvector. And you don't sum the first eigenvector, so from 1 to n. And they knew everything here, and it was a very nice formula. And just analyzing this, they got the nice theorem which I raised. Now, why couldn't we imitate this for general k? Because dual Hahn polynomials tend to be quite nasty for general k. And this is why we could use it for k is equal to n-half, because for k is equal to n-half, we use the recurrence relationship and the difference equation that this dual Hahn polynomials satisfy to get really nice formulas for them. And so it was more easy on the endpoints at 1 and n-half, but in the middle, it's crazy. So I didn't want to confuse you, but just saying that it's a different story.
What is a dual Hahn polynomial?
They're symmetric polynomials that are orthogonal with respect to the stationary measure which I erased. So what happens here is that our matrix is not exactly symmetric, but it is a reversible Markov chain. So remember Pn, and maybe we'll explain this and then I'll stop because. So this was our stationary measure. So so that matrix that I wrote earlier has this nice property that if I start according to my stationary measure at I, and then I take a step according to the Markov chain, that would have been the same as if I had started from J according to the stationary measure and taken a step from I. Why is this important? Well, because this is like saying my matrix is symmetric. It's not really symmetric, but there is a spectral theorem which will say that the eigenvalues of this thing are real, and this thing has an orthonormal basis with respect to this measure. Now, if you know that, if you know the orthonormal basis, if you can find these eigenvectors, that's good. And in this case, they are the dual Hahn polynomials that are orthonormal.
Another stupid question. When you say orthonormal base with respect to the measure, you mean that the highest eigenvalue has an eigenvector which is 1. The eigenvector corresponding to the highest eigenvalue is 1?
All ones.
Okay.
This is all ones.
This is what you mean.
And for the rest that are not all ones, this thing is 0 if I is not equal to j, and this thing is 1 if I is equal to j. Okay. Do I have any time to talk about the lower bound, or shall I stop?
Yes, 4 minutes.
4 minutes. So very, 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 very quickly, just to give an idea of how you would prove a lower bound using these dual Hahn polynomials, which I'm not going to write down because there's no time and probably it's not as interesting. So we have again the total variation distance over there written, and the idea is to find a very bad set that would make this total variation distance big. So maybe you are very likely to be there with respect to the Markov chain, but the stationary measure is far away, or vice versa. Okay, so for that we will use the first eigenvector, and we will actually normalize it, meaning that I want that thing to be 1. And the bad set will be something like, now I don't have enough time to explain this to you, but the values, keeping the values where f of x is, let's say, bigger than some little a, which is defined later on in the paper. And so what happens is that if you find the mean of this function according to the transition matrix, well, this is an eigenvector, and it is also normalized. So, well, the normalized part doesn't come in here right now. The eigenvalue that it corresponds to is this one. So you can just use the eigenvalue. This is the eigenvalue. This comes just because at x is 0, I have this. Okay? And we can also compute the variance of this function similarly. This is more complicated. But still, it uses the first two eigenvalues and eigenvectors. In the same time, with respect to the stationary measure, this is 0. Why? This is exactly your question earlier. The eigenvector corresponding to the eigenvalue 1 is the all ones eigenvector, which means that if here I put all ones, this means that my eigenvector sums to 0. So this is why this is true. And the fact that it is 1 otherwise, if I is equal to j, says that the variance of f is equal to 1. So we need to use an alpha so that according to this measure, this set will be this function is concentrated very close to 0, while with this measure I am around there and I'm far away. So that's the idea and so if alpha is around here, and I want to be bigger than that, then with one measure you have probability 1 of actually being bigger than A, but alpha. While with the other measure you have probability 0. And so this difference up there is almost 1. Just, okay, I'll stop there. I just wanted to pretty much give an idea. And just a small thing is that we have actually treated the case with multiple urns, but I guess there's not much time for it.
Thanks for giving it time. Time for a quick question. So the techniques of so you think if you do k equals 2, can you improve it or?
Now you mean?
Yeah.
No, well, I don't remember the formulas, the recurrence relationship by heart.
Yeah.
Basically, I use the recurrence relationship to say what this eigenvalue, and they're all tiny. The eigenvalues are less in absolute value than 1 over n. And so this thing is actually, for k is equal to 1/2, this is smaller than, after than 3 steps. So in 3 steps you're random. But I didn't write down my recurrence relations, but I can find them and show them.
Well, Evita will be glad to answer questions in private. Thanks a lot. Yeah, unfortunately, I really didn't know.